The deeper the robot descended, the stranger the readings became. Then, hundreds of meters down, the lake floor simply disappeared into a cave no one knew was there. Have you ever wondered what lies beneath your boat once the shore has faded into the distance? Our planet holds lakes so deep and so complex that scientists still haven't fully mapped their lowest passages. For centuries, people who tried to measure them came away empty-handed, which is exactly why they earned the nickname bottomless. Today we'll look at what's actually been verified about these places, the real science, not the legend, and why modern robotic technology still struggles to reach the true floor of some of these lakes. Tsirik-Kel, the lake that never runs dry in the Russian Republic of Kabardino-Balkaria, sits a lake that has puzzled geologists for decades. Lake Tsirik-Kel. At first glance, it looks almost artificial, a pool of vivid turquoise that holds its color through rain, snow, and sun alike. It also refuses to freeze, even in the harshest winters, when nearby streams turn to solid ice. Tsirik-Kel stays close to 9°C year-round, likely thanks to a steady inflow of warmer groundwater. That warmth hints at the lake's real secret. Watch the small river flowing out of it, and you'll notice something odd. Millions of liters leave the lake every single day, yet no river or stream flows in to replace them. There's no visible surface source at all. The explanation isn't magic. Researchers believe the lake is fed continuously by powerful underground karst springs, invisible from the surface, but strong enough to keep the outflow going indefinitely. For a long time, local accounts placed the lake's depth at around 250 meters. When research teams later explored it with deep-water robots, compact submersibles fitted with lights and mechanical arms, those older estimates turned out to be too conservative. As the robots descended, operators on shore expected to see the lake floor appear on their monitors at any moment. Instead, the readings kept climbing, and what should have been a flat lake bed gave way to open, cave-like space. Rather than a solid floor, the robots found a wide underwater cavern branching off to the side and continuing downward. It suggested that Tsirik-Kel isn't simply a deep pit of water, but the visible entrance to a larger network of flooded passages running into the surrounding mountains, a system that, even now, hasn't been fully mapped end to end. At those depths, the water stays clear, but very little light survives the descent. So much of what the cameras capture appears close to black. Divers and researchers have compared it to searching a pitch-dark forest with a single flashlight. Technically possible, but limited by how far the light can actually reach. That kind of depth also comes with real physical stakes. At around 300 meters underwater, pressure is roughly 30 times what it is at the surface, intense enough that only specialized, pressure-rated equipment can survive the descent, and human divers can't follow past a fairly shallow point. Despite everything hidden below, the lake itself still looks calm and almost sleepy from the shore. Its bright blue surface, giving no hint of the scale of what sits beneath it. Exactly how far the underwater system extends beyond what robots have already surveyed remains an open question one researchers are still working to answer, rather than one anyone can currently claim to have solved. Lake Bezdonnoye, a local legend worth investigating. Outside Moscow, in the Solnechno-Gorsk district, sits a much smaller lake with an outsized reputation, Lake Bezdonnoye, Russian for the bottomless lake. It's an unassuming, round pond in the forest, only about 160 meters across, small enough that most visitors assumed they could swim across it without much trouble. Yet, according to local accounts passed down for generations, this modest lake once stumped two well-known figures from Russian history. Local legend holds that the chemist Dmitry Mendeleev, who had an estate nearby, tried to measure the lake's depth himself after hearing how uneasily residents spoke about it. Around the same period, the poet Alexander Blok is said to have written in his diaries about local claims that the lake was somehow connected to the ocean. It's worth being clear about the sourcing here. These stories are widely repeated online, but the historical record behind them is thin, and they're best treated as regional folklore rather than confirmed scientific history. As the story goes, Mendeleev tried the simplest method available: a rowboat, a long rope, and a heavy weight, hoping to settle the question once and for all. According to the account, the rope kept feeding out, meter after meter, until the entire 100-meter length was gone with no bottom found. Whether or not every detail of that particular telling is accurate, the underlying claim is easy to test today. And it points toward a real geological phenomenon worth exploring next: why an ordinary rope and weight measurement can fail completely in certain lakes, even when the lake itself is nowhere near as deep as the story suggests. One local legend even claims that shipwreck debris once surfaced in the lake, including a plank supposedly bearing the name of a vessel that had sunk far away in the Atlantic. There's no historical evidence behind this, it's folklore, plain and simple, the kind of story that grows naturally around a lake with an unclear depth. What is true is that traditional weighted line measurements at Bezdonnoye have often produced confusing, inconsistent results, which is exactly the kind of gap that folklore tends to fill in. Researchers have since offered a much more grounded explanation: a false bottom. In many peat-rich lakes like this one, water gives way not to solid ground, but to a thick, waterlogged layer of decayed plant matter and silt that has built up over centuries. Depending on its thickness and density, this layer can be dense enough for a light object to rest on top of it, while a heavier weight may sink further in, though how far and how consistently depends on local conditions rather than following a fixed rule. This is a well-documented feature of peat bogs and boggy lakes more broadly, even if the exact structure beneath Bezdonnoye itself hasn't been independently verified in detail. What we can say with confidence is that this kind of soft, layered sediment is enough on its own to explain why a simple rope and weight approach struggled here for so long, without needing to reach for tales of oceanic tunnels to account for it. Underground rivers and the Swiss cheese planet it's worth remembering that the ground beneath a lake isn't always one solid slab of stone. In karst regions especially, it can be closer to a wheel of Swiss cheese, riddled with channels and voids. This is well-established geology. Water dissolves soft limestone over time, carving out cave systems that can connect one lake to another, or to a river, or to caves far from the surface. Where this really complicates measurement is when a lake's basin connects to those hidden channels. A weighted line lowered straight down doesn't always meet a flat, predictable floor. Depending on underwater currents and the shape of submerged cave openings, the line can drift off a straight vertical path and catch on a ledge, or slip into an opening in the rock, well before it reaches what most people would call the real bottom. It isn't that the rope slides sideways on its own, it's a combination of current, rope angle, and the uneven shape of the cave system beneath it. That combination is enough to explain why certain lakes carried a bottomless reputation for so long before modern sonar came along. Researchers have used harmless dye tracers to study where these hidden channels actually lead, and the results have been genuinely striking. Dye released in one lake has, in documented cases, reappeared later in springs some distance away, confirming that these systems really do connect across the landscape. Mapping them fully is difficult, and often incomplete cave divers and sonar teams have made real progress in many systems, but difficult isn't the same as impossible. What these connections do mean is that a lake's deepest measured point may not be its true geological limit at all, but simply the point where a line first meets an opening into a much larger connected system. The Hranice Abyss, Europe's deepest flooded cave. The Hranice Abyss, in the Czech Republic, is a real and well-documented case of a lake outpacing its own measuring equipment. On the surface, it looks like a modest forest lake sitting inside a limestone sinkhole, but it holds the deepest confirmed flooded cave system currently known anywhere on the planet. In 2016, a research team lowered a tethered robot into the abyss as part of a genuine documented expedition. The robot reached 404 meters, not because that's necessarily the true depth of the cave, but because that's where its cable ran out. The robot itself couldn't see hundreds of meters further down. What it could do was confirm that open space continued well past the point where its tether stopped it from going further. Later depth estimates, based on geophysical modeling and additional survey work rather than direct measurement, put the abyss at somewhere around 200 meters, a figure that should be understood as a scientific estimate, not a confirmed measurement. For scale, that's deeper than 2 Burj Khalifas stacked on top of each other. The water at depth is also known to carry unusually high concentrations of dissolved carbon dioxide, which creates real challenges for divers primarily around gas management and decompression, alongside general visibility, rather than simple skin irritation. It remains one of the clearest modern examples of a place where exploration technology is still actively catching up to the scale of what's actually down there. Karst lakes, the kind connected to underground cave systems, don't always behave like simple, closed basins. Depending on groundwater pressure, water can drain out through submerged sinkholes at the bottom of a lake, and in some cases that flow can later reverse, with water pushed back up from below. This is a real, documented feature of karst hydrology, driven by changes in pressure within the connected cave system, rather than anything happening on the surface. At the point where water drains downward through a submerged opening, currents can strengthen, and that current is exactly what makes diving near these openings genuinely risky, not because of some giant invisible force pulling boats toward the center, but because a diver who gets close to a draining sinkhole can be pulled into a narrow passage they didn't intend to enter. That risk is well documented in cave diving circles and is treated with real seriousness by anyone exploring these systems. When groundwater pressure shifts and that flow reverses, some karst springs and lakes can begin pushing water back out instead of taking it in. It's a genuine phenomenon in karst hydrology, though claims about it regularly bringing ancient debris to the surface. Or about a lake's measured depth changing dramatically from one visit to the next, go well beyond what's actually documented and shouldn't be presented as typical behavior. Modern expeditions, robots, sonar, and careful analysis exploring lakes like these takes far more than a boat and a fishing line. Modern expeditions rely on tethered underwater robots, remotely operated vehicles, or ROVs, fitted with cameras, lights, and sensors that can maneuver through narrow, flooded caves at depths no diver could safely reach. These robots measure temperature, water clarity, and chemical composition as they descend, feeding that data back to the surface in real time. Alongside them, research teams use multi-beam sonar to send sound signals into the water and build three-dimensional maps from the echoes that bounce back. This part of the process is genuinely high-tech, but it isn't automatic. Sonar data doesn't reveal hidden caves by itself. It takes trained researchers working carefully through the raw data to interpret what an unusual echo actually represents: a side passage, a ledge, or simply a change in rock texture. Much of the real work in an expedition like this happens during that analysis, long after the equipment has already come back out of the water. Life in the dark. Given the cold and total darkness at these depths, it would be reasonable to expect nothing living down there at all, yet some cave systems do support life, adapted in striking ways to permanent darkness. The clearest examples are small crustaceans that have lost their eyes entirely over generations, relying instead on long, sensitive antennae that can detect the faintest movement in the water around them. Blind cave fish exist in some systems too, though it's worth being clear that many deep cave lakes contain very little life at all, or none that's been documented. These adaptations aren't something found everywhere. In a number of isolated cave systems, researchers have identified species previously unknown to science. That's a genuinely exciting result on its own, distinct from, and often confused with claims about rediscovering species thought to be extinct. And while these isolated ecosystems are remarkable for having developed largely apart from the surface world, that isn't the same as being frozen in an unchanged original state. Evolution doesn't pause just because a species lives underground. The real challenges of deep cave exploration, some of the most persistent difficulties in exploring these systems, come down to ordinary engineering limits rather than anything mysterious. Radio signals already struggle to travel through water under normal conditions, so signal loss at depth isn't unusual or unexplained, it's expected. When a camera feed cuts to static or a connection drops, the cause is typically a damaged cable, a loose connector, or ordinary signal attenuation over long tethers. The same kinds of failures that affect underwater equipment everywhere, not evidence of some undiscovered force at work. Equipment does occasionally get lost on these expeditions. A cable can snag on a sharp underwater ledge and snap, leaving a camera or ROV behind for good. This has happened on documented cave diving and ROV expeditions, though it's the exception rather than a routine hazard scattered across many lakes around the world. When it does happen, it's simply a reminder of how physically demanding these environments are for equipment, not a sign of anything unexplainable happening below the surface. Even with today's satellite imagery, high-resolution sonar, and remotely operated vehicles, there are still cave systems beneath ordinary-looking lakes that haven't been fully mapped. We can survey much of the ocean floor in detail, yet a narrow, flooded cave entrance can still take years of careful, incremental exploration to understand. Not because the science is mysterious, but because the environment is genuinely difficult to work in. Some expeditions do reveal new passages leading further into a system. Others simply confirm where a cave system ends. Both outcomes are valuable. What lakes like these really demonstrate is how much patient, careful work goes into mapping even the parts of our world that are physically close to us, hiding just beneath a calm, unremarkable surface.